Good.
Writing a big book, at least looks, at least to me, like, building a house. Right? What do you think?
Well, yeah, in retrospect, I don't know that such a big book is what people want. I think a lesser amount of pages is perhaps more appealing. On the other hand, as I mentioned, there's a lot of value to myself for my future research. So some of the details that I have put in there have been of lasting value, and so in some sense I'm writing parts of the book for myself. I think there's definitely a happy medium there of how much material is wanted. It's interesting in random matrix theory, there have been some initiative made in just brief introductions that have been quite popular. So it's different markets out there. The other reality with my own book was that in the beginning, my area was not random matrix theory. It's Coulomb gas, log gas. Random matrix theory was an emerging field during that period of time, and the focus changed quite a bit.
And next year, Song-Su and I will organize a random matrix theory conference in Jeju Island. So if you are interested I will invite you to this lovely island.
That island's well known even in Australia. It's very kind. Depending on my schedule, I'd hopefully haven't made my first trip post COVID yet, but let's say getting better endurance, and my boundary conditions, if you want to call it that, are improving. So let us hope that very kind invitation can be taken up. So I know you're all very active in seminars, conferences generally. So it's to be very good for the broader community.
Okay, I think it's time to start. Okay, I'm delighted to introduce Professor Peter Forrester as a distinguished speaker of the Kias-Spengler series in mathematics. His research primarily focuses on mathematical physics, particularly in the field of random matrix theory and related areas of statistical mechanics. The seminal work, log gases and random matrices, which is a comprehensive about 800-page long monograph published by Princeton University Press in 2010, is widely recognized as a masterpiece in the field of random matrix theory. Throughout his illustrious career, Professor Forrester has received numerous accolades for his contributions, including the Medal of the Australian Mathematical Society in 1993, election to the Australian Academy of Science in 2004, and several Australian Research Council personal fellowships. From 2012 to 2014, Professor Forrester served as the president of the Australian Mathematical Society, which highlights his esteemed position as a leader in the Australian mathematical community. Surveying the rapid progress of the field of random matrix theory after 2010, Professor Forrester recently co-authored a book on non-Hermitian random matrix theory with Dr. Song-Su Byun, a member of the Center for Mathematical Challenges at KIAS. In two distinguished lectures, one today and the other next week at the same time, Professor Forrester will present some aspects of this monograph. Let's extend our warmest welcome to Professor Peter Forrester.
Well, thank you everybody for coming along to this lecture. I'm extremely fortunate to be able to be in this position to give the lecture. I thank Professor Kung for the opportunity. The opportunities come about through my collaboration, as was mentioned there, with Sang-Soo Bien, where we've gotten together, pulled our different knowledge base in the field. My knowledge base, as Professor Kung said, there goes back a number of years. In fact, chapter 15 of my book on log gases and random matrices relates to the material of this this lecture and indeed our monograph, whereas Sang-Soo, very early career researcher, he's really at the forefront of new research in the topic, and I think it's been a very good combination, pairing to put together a couple of 100 pages in remarkable time due to Sang-Soo's work ethic, and both of us together complementing each other. We now have submitted to the KS series a book called Progress on the Study of Ginibre Ensembles. All right, let me indicate a little bit about the book to start with. You can see that I've got the different chapter headings of the book written down. Now, I'm going to be rather modest in these two lectures and focus on some beginnings relating to eigenvalue probability density functions. So why I'll be talking about eigenvalue probability density functions? Because our title of our book is Ginibre Ensembles. Ginibre ensembles are a class of non-Hermitian random matrices. And in fact, there are three types of Ginibre ensembles. And in our book, part one considers the type where the matrices have complex entries. Part two, where the matrices have real and quaternion or quaternion elements, which I'll explain soon. I will indicate the foundations of these ensembles through a summary of Ginibre's paper as we go, and that will also then take me to the beginnings of our chapter here on eigenvalue statistics for GIN-OE and GIN-SE. After that, my objective is to give away, if you like, my own background in the field, which is actually in statistical mechanics, and concentrate on statistical mechanics aspects of the model that superimposes this GIN-UE, and it's called the two-dimensional one-component plasma. Let me continue. So I should say what we've done in our preface, it's really important, and it's very I think recommended for all of us to pause every now and again and pay some sort of homage to those who've made it possible, if you like, for us to actually get in this field. And I'll begin with Sang-Soo. So Sang-Soo began his studies very recently, PhD 2017 under Professor Kung, and obviously learns a particular skill set there. Professor Kung's known complex analysis, conformal field theories, applications in statistical mechanics, and SLE. And that was supplemented during a sort of good fortune partnership between Germany and Korea, where Sang-Soo was involved with Professor Ackerman, and Professor Ackerman's working on really two-dimensional supported random matrix ensembles with application to QCD, and he's also known for this recent work on relatively recent work on random matrix products. So Sang-Soo begins with a blend of this knowledge set, and of course builds up from that his own particular strengths and insights, starting 2017 and really taking off in the last few years. Myself, well, quite classical. I'm really now an historical figure in the field, I must say. 1982 was when I did my master's under Professor Edgar Smith. His interests were in the theory of fluids with long-range forces. So that's very much Coulomb systems, electrolytes, and such things. With my PhD, I actually studied under Baxter at Australian National University, a well-known mathematical physics for Yang-Baxter equation. Interestingly, in his own PhD, Baxter did study the one-dimensional Coulomb gas, but that wasn't his interest at the time that I was there. I was working on his interests in phase transitions of models in two dimensions, lattice models. But just like Sang-Soo, I had a type of mentor as well as a primary supervisor during my PhD, and that was Jankovici at Orsay, and he was a Coulomb systems person. And continued my interest from my master's time studying Coulomb systems. As Professor Kung said, and we were chatting in the beginning there, over a long period of time, 15-year period, I found that there was some really interesting material that I was studying at the time. And I must say I was concerned that it would somewhat be forgotten. So one way to record the material was to actually take the initiative to write a book. And I had the fortunate opportunity of having a number of research fellowships and not having full lecturing duties. So it was gave me that little bit extra time. Now, the final chapter of this very long book, chapter 15, is entitled Two-Dimensional One-Component Plasma. And that's what relates to these Ginibre ensembles. So that was a little bit about how we got to start in this field. And it's extremely important. Who knows what might have happened to either of us if we hadn't have had this beginning. But here we all are. And now we're associated, all of us, nearly all our audience members are associated with some, let's call them big names in mathematical physics. So we'll start with Ginibre. So Ginibre at Orsay, I mentioned my associate with Jancovici. Jancovici's office, the next floor up, statistical mechanics, and then the high energy physics people. When I visited Orsay in 1985, Ginibre very prominent on down the next corridor, although I didn't talk to him at a scientific level. I very much walked past his office nearly every day down to the tea room. Okay, we have F.J. Dyson here, foundational studies in random matrix theory at the very beginning of the 1960s. And we have Wigner, Eugene Wigner. And there's also an interesting, I mentioned Jancovici. Jancovici actually studied under Wigner as part of his own PhD. So there's quite a network here. That's our random matrix theory. And I'm going to talk about the beginnings of random matrix theory and how Ginibre's paper fits into these beginnings of random matrix theory. So there'll be this interplay between Ginibre's work and that of Wigner and Dyson. And as I mentioned, as far as the direction of this lecture goes, it's going to focus on the two-dimensional one-component plasma, which in some sense overlays the one of the Ginibre ensembles. That will be part B of the talk. Let's begin indeed with Ginibre's paper entitled Statistical Ensembles of Complex and Quaternion and Real Matrices. So the three different ensembles there. Interestingly, we see at the time Ginibre's address is at Princeton, same general location as even though Dyson was at the Institute. Wigner, they're all around Princeton, no doubt. So maybe random matrix theory was being talked about and was a topic of some interest. What did Ginibre actually do in a hands-on sort of introduction here? Well, we'll take a square matrix, we'll fill the square matrix up with standard normal distribution random variables. After we've done that, we'll compute the eigenvalues. So I've got here an example of 5 by 5 matrix, compute the eigenvalues. You can see in this example that there's actually to numerical accuracy at least, a real eigenvalue present. The other eigenvalues occur in complex conjugate pairs. What could we do now in modern software? We can easily plot the result of many such computations. And we're going to, with being wise after the event, do a bit of scaling here of the original matrix by this 1/√n factor. We're going to superimpose a unit circle. And we see some sort of uniform distribution within this unit circle and thinning eigenvalues outside of it. And we also see quite clearly the accumulation of eigenvalues that are on the real line. So what we want to do is study some statistical mechanics associated with that. And we claim that over the years, the relevance of this ensemble has become more and more prominent. And that's really the only way myself and Sung Soo have been able to get a market, if you like, because there is a lot of interest in this class of random matrix. We continue the three ensembles. What happens in the complex case? Well, we have a real part and imaginary part. Again, independent standard Gaussians. As far as illustrating the quantities of interest, same sort of thing. We want to generate a sample. And here again, n equals 5 has been chosen. Want to compute the eigenvalues. So very simple using software. We make an observation. Eigenvalues are no longer be real, and they no longer will occur in complex conjugate pairs. So there's some distinction between the real case and the complex case. But we do see something in common as well, and that is this close to uniform distribution inside the unit circle after some scaling. Real case, complex case, fairly familiar. We come to quaternion case, a little bit less familiar. What do we mean by quaternion case? Well, we're actually talking about a complex realization of quaternions. It's fairly well known that this 2x2 structured matrix realizes a quaternion in an algebraic sense, and enables us to actually talk about random matrices, because we can do the usual sort of thing, generate the matrices. Once we have complex numbers, makes sense for us then to ask about the eigenvalues as before. So we can do that, generate random matrices. We can illustrate the result of the calculation quite easily. And we see some, again, distinct features and some things in common. The distinct feature here is a repulsion from the real line, whereas remember in the real case, we actually had an accumulation on the real line. On the other hand, if we superimpose the circle, we have a particular scaling. We do see something close to a uniform distribution in these different halves. What would I like to point out next? Well, I'd like to point out next that when we've described these matrices through the distribution of individual elements, we can actually form the joint distribution, which is the product of all the independent distributions, and write it in this matrix form. So that's an identity, and all of them can be written in the form either the minus up to some proportionality, the trace of x dagger x, where x is our matrix. That's something to keep in mind as we progress. What studied Ginibre's, what motivated Ginibre's study back in 1965? Well, so one of my our colleagues in the field, Ken Zipia, actually emailed Ginibre and asked him this question, and his answer was that he was motivated by mathematical curiosity, he called it. So he wasn't, being a mathematical physicist, a question could be, and did he already have in mind some applications, for example, to non-Hermitian quantum mechanics? You know, was he that far-sighted? Non-Hermitian quantum mechanics is a very popular topic come the 2020s, but perhaps not back in the 1960s. And no, the answer was that it wasn't actually, it didn't have any physical model in mind. Nonetheless, he very much was aware, and this will be part of my the thesis of this particular lecture, that he's very much aware of the earlier work, and that there is quite a lineage between the earlier work of Wigner and Dyson and Ginibre's studies. Why do I put this sort of thesis forward? Well, I don't think I'm the only one that would join the dots. Let us go back to one of Dyson's foundational papers, Dyson's threefold way. And Dyson was very much motivated by problem in mathematical physics or theoretical physics. He wanted to consider what he would call a complicated or complex quantum mechanical system in a statistical way. He wanted to reduce down to the essential aspects of that statistical description. And he realized that he could catalog quantum mechanical Hamiltonians in a statistical sense through their time reversal symmetry. So he had that insight. And, time reversal symmetry, the simplest example of a time reversal symmetry is just complex conjugation. Technically, time reversal symmetry is an anti-unitary operator. So in this very first case, there's two classes, as it turns out, of these anti-unitary operator. It depends on whether there's spin present in the system. So t squared equals 1. Again, and if we take complex conjugation, we apply it twice, we get back to where we started. So that could be a model of this t squared equals the identity. And again, with complex conjugation, it's immediately obvious to us that this Hamiltonian should have real elements. That can actually be turned into a theorem where we don't realize the time reversal symmetry is complex conjugation. We realize it in this algebraic way here, as well as it being anti-unitary. And the theorem is that you can always choose a basis that the Hamiltonian has real entries. Dyson understood that point and put this forward as a principle. As I say, he considered the second class of time reversal symmetries and found that the implication for the Hamiltonian, this is the Hermitian, otherwise Hermitian matrix, would be that the blocks, these 2x2 blocks, it could be written in a 2x2 block form with quaternion elements. Again, a theorem that he proved. And without any time reversal symmetry, generically this matrix form of the Hamiltonian will have complex elements. So this is foundational in quantum mechanics and random matrix theory and how they fit together. After that, it's a choice in the Hamiltonian formulation, a choice of a weight on the space of matrices. So there is no normalizable invariant measure on Hermitian matrices. So it's necessary to weight the matrices. Now, the weighting had a certain requirement, and that is a particular invariant. So we recognize this trace. Before we had the trace of X dagger X, where X was our Ginibre matrix. Here, the matrix is already a Hermitian, so it's trace of H squared. But there is some very special properties of choosing the trace of the random matrix. And that was also part of Dyson's strategy, although he did deviate a little bit at this stage. He wasn't happy that this particular weighting is not unique. And in fact, he considered what ensembles of unitary matrices called circular ensembles that will come up later in this lecture. Nonetheless, it's still part of his series of papers, and it's the most logical way for us to continue. The scale factor here, it's a bit innocuous, but nonetheless, it comes up. It's got more importance later. It shows itself in this beta variable now called the Dyson index, and takes on the values 1, 2, and 4. And from Dyson's theory, the 1, 2, and 4 can be regarded as a number of real parts from these complex, these number fields. So the number of real parts of a real, well, that's almost a tautology, that's 1. But for a complex, make this question has a content 2, and for quaternions are actually 4 real parts. Now that is also true in the Ginibre case, but the parameter beta doesn't occur in all the same places. A little bit of a detail there. Let me summarize in tabular form the relation between the foundational study of Dyson and the non-Hermitian variant that was carried out by Ginibre in 1965, a few years after Dyson's foundational paper. So we have this Dyson index that I've just mentioned. It's just in one-to-one correspondence with real, complex, and quaternion entries. By choosing the weight to be a Gaussian, we have a particular invariance. So the distribution is actually unchanged by conjugation by a certain class of unitary operators. Now, in quantum mechanics, that's regarded as a type of basis invariance. And that's a good thing to have in one's ensemble theory. And the invariances are, so what we're saying, if we put this, substitute this into the exponential of the minus trace of H squared, nothing, we get unchanged weighting. And it's the same for the actual measure itself. And that class of unitary matrices is actually real to stay within the real symmetric matrices that occur when we have real entries. We require these matrices to be real orthogonal. That gives rise to the name of the ensemble, this Gaussian orthogonal ensemble. It's because the invariants of the unitary matrices are the orthogonal matrices. And we can similarly do that in all 3 cases. And we get the class of unitary matrices appearing in this invariance and the class of unitary symplectic matrices appearing in this invariance. And that gives rise to these names, GOE, GUE, and GSE. Now with that table, I suppose I could associate this Dyson index, but Dyson index has further meanings beyond just the number of real parts. So it's not done in the theory of Ginibre ensembles to associate beta equals 1, 2, and 4, or it needn't be done anyway. If it is, it needs to be with qualification. So I'll leave that out. But otherwise, there is indeed a one-to-one correspondence, except when we come to the invariance, we're no longer dealing with Hermitian matrices. We actually have a bi-invariance here. So we can have left multiplication or right multiplication. but the same class of matrices. So here it's very much one-to-one correspondence. Orthogonal here, orthogonal in the Ginibre case, and it's regarded as standard now for us to denote the real class of real Ginibre matrices by Gin OE. The O because of this invariance here. Highlights from Ginibre's paper. Yeah, well, I just put down the title and the abstract. To progress this lecture, I do need to highlight certain features. And in fact, it's valuable to highlight these features. And it's, to say one more time, the sort of thesis of this particular lecture, that highlighting aspects of Ginibre's paper, we can see the lineage from the earlier work, and it can also suggest to us future problems, some of which have been solved. Let us begin. So in my simulations, we defined the random matrix through the elements of having normal distributed independent elements. Then we went ahead and computed the eigenvalues on the computer. Well, what we'll do analytically for that task, or algebraically, is we're diagonalizing the matrix. Where I've got this decomposition involving the diagonal matrix of the eigenvalues and the eigenvectors. Now, for a non-Hermitian matrix, things are more complicated than the Hermitian case, because our matrix of eigenvectors won't be unitary. Nonetheless, so in earlier work on the Hermitian case, here, this would be a unitary matrix, and that's actually a simplification. Without it being a unitary matrix, it's actually a technically difficult calculation that Ginibre managed to carry out to integrate out the dependence on the eigenvectors. Very challenging. Nonetheless, the final expression is quite compact and very beautiful for those in the field. It has a lot of structure. So we have in front of us this joint up to proportionality, this joint PDF for the eigenvalues. We see this exponential term, Gaussian term, that's just coming from diagonal, just substituting in. Well, it's not quite just at all here, because that's actually a complicated step. If we substitute this into the e to the minus trace g dagger d, we still have to integrate out over the eigenvector. So we don't get this for free. Whereas we do get this for free, this term for free in the Hermitian case. Nonetheless, it comes out to be simple. And this term here, it can be shown to be the Jacobian coming from the eigenvalue part, which does factorize when we change coordinates to this eigenvector and eigenvalues. So this is the expression that we're going to say more about, and please keep it in mind. In Ginibre's paper, he makes the observation that this can be written in what we call Boltzmann factor forms. So something from classical statistical mechanics, when we see an e to the minus b to u, we can interpret this u. If we can interpret this u as a potential energy, then we have a Boltzmann factor viewpoint, or a classical statistical mechanics viewpoint. Well, for potential energy to be easily interpretable, we want to consist of just one and two body terms. And let's write this in an exponential form and see what we get. Well, we get a harmonic attraction to the origin, and we get pairwise logarithmic repulsion. What's the deal? Why would logarithmic be particularly interesting in statistical mechanics? Well, it is particularly interesting because it's the solution of the two-dimensional Poisson equation. So we're in the plane, and we have the solution of two-dimensional Poisson equations. So we have a bona fide Coulomb gas, the correct Coulomb gas, the correct potential for the dimension. And I make that comment, and Ginibre made that comment in his paper. Let me say a little bit more about the Coulomb gas, because that was really my beginning in the field. This two-dimensional one-component plasma, the way of thinking, and it really, comes from nuclear matter, really, that the electrons can be regarded as a cloud, and the protons as actual mobile particles. That's the viewpoint. One has to be in a regime where potential energy dominates from the kinetic energy to be able to get the classical classical behaviors, but there are such regimes. So that's really the viewpoint here. We have a smeared out background and we have mobile particles within. And from that viewpoint, we can actually do calculations to compute the total energy. Remember, in statistical mechanics, this here is the total potential energy. It consists of particle-particle, which is the logarithmic interactions between the particles, but also consists of an energy term between particles and the background. And that's what I'll want to indicate gives rise to this harmonic attraction towards the origin. It's a well-defined calculation on how to actually do this. We have this solution of the Poisson equation. We have this smeared out background with charge density, normalized it here to be -1 on pi. We have to integrate over this solution of the Poisson equation. If we do that, it's a straightforward calculation, we get out precisely this harmonic term here. So that's the physical interpretation of this term that appears in random matrix theory by studying the eigenvalues of Gin-UE class of matrices. Thinking of it as this Coulomb gas. I point out here, the same as Gin-UE. Well, we do get some extra terms here, which come up later in our studies. These are just constants. For random matrix theory, we have a probability density function. We want to normalize it. But in statistical mechanics, we really want to start with the Baire-Boltzmann factor. The Baire-Boltzmann factor up to proportionality is given as it is in Ginibre's studies, with a particular value of this inverse temperature. I should also emphasize it's the inverse temperature is a very special value, sometimes called for other reasons I won't have time to go into. It's also called the free Fermi point, beta equals 2. Indeed, Ginibre made that observation, but he didn't make that observation in isolation. Before him, Wigner in the late 1950s had made this observation for GOE, which was Wigner's interest and one of his contributions to random matrix theory to introduce this ensemble. And in particular, Dyson made a big deal of this Coulomb gas type interpretation in his series of papers in the very early 1960s. The reason is that if we go back to the Gaussian ensembles of Hermitian matrices that I made mention of and ask the same question, what is the eigenvalue probability density function? Do the computation, much simpler computation than what Ginibre had to carry out, because as I mentioned, you get for free change of variables in your weight is just the sum of the squares of the eigenvalues for the Hermitian matrices, not true for the non-Hermitian case. Yeah, it was known there, but why the beta is more significant in this viewpoint in the case of the Gaussian Hermitian ensembles is because the interpretations of the temperatures, whereas we have one special coupling for Gin-UE, we actually have 3 special couplings in the case of the Hermitian ensembles that all fit the same pattern. What we're going to be doing next in following Ginibre's paper is asking about the joint eigenvalue distribution in his 2 other ensembles when we have real entries or when we have quaternion entries, and we find that this pattern breaks down, that it is present in the Hermitian case. We have 3 special couplings. Well, we can call this one the free Fermi point, and we'll see it relates to determinant point processes. For those in the know, these other 2 are outside that class, and they relate to the Faffian point process. And that's very much in common, actually, with Ginibre's other 2 ensembles. And it's something that Sung-Soo has made quite a bit of in his own research work and others. So it's a lot of structure out there in the more complicated, let's say cases where there are Faffian point processes. So let's go to the first of those in Ginibre's papers. Ginibre was not aware, and I don't think anyone was aware at this stage in the 1960s that there were these Faffian point processes. That took a little bit of developing, and I think perhaps in a paper that Dyson wrote in about 1970, he introduced this concept of a quaternion determinant, and he was able to show quaternion determinantal structures, and one of his theorems was a quaternion determinant can be written as a Pfaffian. It turns out the quaternion determinant, and I think in the commentary that Dyson wrote in his own collected works, he said he worked particularly hard to discover this structure, and he was a little bit disappointed that it didn't, let's say, explode interest, although I just think the time frame's a little, just took a little bit longer. And that's a common feature of even Ginibre's paper will come to, and the take up of Ginibre's paper, it's really very prominent now, but it took a while. So that was the case of these extra structures. All right, let's go, as I say, go to the first of these additional structures by asking the question from Ginibre's paper, or revising from Ginibre's paper, the eigenvalue PDF in the symplectic case. So the functional form does not follow the earlier pattern. It's not just, so if we regard this as a beta equals 4, we don't get the fourth power of the product of differences. We actually get involved here, there's differences with some complex conjugates in there. Remember, from our plot, we do have for every eigenvalue its complex conjugate. We have this repulsion from the real axis. And if we interpret, if we have that picture in mind, it's quite straightforward to give a plasma analogy in this case here, and it involves image charges. So that's a very legitimate Coulomb system. A big theme in the study in Coulomb systems is their boundary condition. Whether we have a Dirichlet or Neumann type boundary condition, this is regarded as a Neumann type boundary condition. What are we missing? We're missing the, no, jumped here. Okay, so we are missing the real case. I will come to it, but following in Ginibre's paper, I should point out that K-point correlation function was another contribution he made, and I have been talking about that on the previous slide. In the Ginibre case, complex entries, it gives rise, if we have a sort of fluid interpretation now of our particles, statistical mechanics interpretation, and a very natural question is to ask about the correlation functions. Dyson had earlier done that, as I'll indicate. And Ginibre found and made specific what the actual point process by describing it in terms of its correlation functions is for this Ginibre case. Wrote down this closed formula for this general K-point correlation. This general K-point correlation coming from integrating over all but K of the variables with the joint eigenvalue PDF. Now, the defining feature of a determinant point process is that there is a determinant of a single function of two variables called the kernel function. And Ginibre has specified this particular kernel function, and it's very structured, and it gives rise to this class of special functions, this here being the incomplete gamma function, written in its series form here, partial sum of the exponential power series. He was able to prove, as a consequence from this formula here, the theorem we hinted at by our numerical simulations. So this is after the appropriate scaling. So as a matrix, we would scale by 1 and root n. In this limit formula, we actually multiply by 1 and root n, and we let this z variable have its modulus just less than 1. He made note that we obtained this particular limit formula, where this is the spectrum in these, what I call, we'll generally call in random matrix theory, a global scaling. So we're in a compact support. The deleting order in this limit theorem has 0 as the density outside of this boundary of the disk, and within the disk, it's uniform. So that's contained in Ginibre's paper, and it's very striking visually when one does a simulation of this result. But back in 1965, that's been a theme of some significance in probability theory of the last 15 or so years, proving this theorem for a general class of non-Hermitian random matrices with IID variance 1, but otherwise no restraint on the class of IID variables. What else is in direction to Ginibre take? Well, in statistical mechanics, the global density is not the most natural density to take. The limiting density, limit to take, the thermodynamic limit involves constant density. It's a constant density in the scaling of the eigenvalues as or the Ginibre ensemble. We don't put any n dependence in front of our variables. We just ask what's the large n limit. And that is giving us what we see here, a density, which is 1 on pi, a fixed number. So it's not going to 0 as it does in the global density scaling. So knowing the limiting form of the correlation kernel, we can write down the easy to interpret lower order correlation function. So we have a 1 on pi, as I just mentioned, for the density of the eigenvalues, which, since we're going to be saying more about it in the Coulomb gas language, is actually equal and opposite to the background charge density. In the Coulomb gas viewpoint, we've imposed a smeared out background, and upon that, we have our mobile particles. We require equal and opposite density. It's a sort of a principle in Coulomb systems for stability. And indeed, mathematically, that's what comes out. Harder to interpret is, to anticipate the actual final result, I should say, is what is found for this 2-point correlation function. 2-point correlation function, we can regard as a conditional density. We fix one particle at W, and then we ask about the density about that one particle. That's related. If we again divide by its density, it precisely has this interpretation of this quantity here. So we find to leading order just the product of the densities. And the non-trivial term, sometimes called the connected part of the 2-point function, actually falls off like a Gaussian, which has surprised everybody really in the Coulomb gas world. In the Coulomb gas world, there is what's called a weak coupling theory, high temperature theory called Debye-Huckel theory, and there is a correlation length, and that gives rise to exponential decay. And to see a Gaussian decay has been something that's disturbed a lot of people, and people have been trying to explain. There is some speculation that it's the only coupling that is non-exponential. That's never been proved. It's quite a mathematical challenge to inquire about what's called the correlation length in the plasma viewpoint. Well, excuse me there, escape. I hope that, that was just my own screen changing. Let me emphasize or draw attention to earlier calculations along the topic of point processes, random matrix ensembles, and determinantal structures. The first statement of what we just saw in Ginibre's paper that I know about is when Dyson inquired about one of his members of his circular ensemble. This is an ensemble of random matrices known in historical times to Weil back in the 1930s. Weil asked the question, and he realized that there is unique invariant measure on the space of classical group of unitary matrices. And in his studies, he actually computed what the corresponding eigenvalue probability density function was. And Dyson later reclaimed this result and some other related results, but this can take to be as a starting point. So here, everything is on the unit circle because we're dealing with random unitary matrices. You can ask the question, what are the corresponding k-point correlation functions? And that question was asked by Dyson, and he found the distributions in the finite case and the bulk scaling limit. And for the bulk scaling limit, it's worthy to pause a little bit. The expression he got, if we specialize to the 2-point function, is quite distinct from what we saw before. I emphasized, we had this Gaussian decay in the bulk of the Ginibre ensemble, whereas for this class of unitary matrices, which happens to be in the same universality class as the Gaussian unitary ensemble in the bulk, we get a an algebraic decay, and we also have an overlaying oscillation. So something that we just do not see in the two-dimensional case. And I would like a sort of a theory, relating to that. And, I think it's quite well known how to anticipate this in later years. Last of the Ginibre ensembles, the Ginoe, when there are real entries, we saw in our simulations that real eigenvalues can occur. Now, mathematically, that means things are a little bit more complicated because there are different sectors in the probability density function for the eigenvalues. It's not absolutely continuous. So depending on what sector one's in, one has a different analytic expression. Ginibre was able to actually find the analytic expression in the sector where all the eigenvalues are real, and he gave precisely this joint PDF in that case. So what's some consequences of that? Well, this is normalized. What's the meaning of integrating over this sector? Well, the meaning of integrating over this sector is giving us the probability that all eigenvalues are real. And that's actually a calculation Ginibre could have done in hindsight, because it was already known how to normalize, because this same factor appears in the question of what is the joint eigenvalue PDF for GOE, that is real symmetric Gaussian matrices. That was known to, or made use of, using other earlier work by, as I mentioned, Dyson and Wigner, and the normalization is known there. So since we can therefore integrate over this, if we integrate over this expression, we get 1. If we integrate over this, we substitute in this product of gamma functions, we do some simplification. We could read off immediately from Ginibre's paper what the probability of all eigenvalues being real is. This is the expression here. Actually, this was written down for the first time in a paper of Edelman. There we go. So I've taken a little bit of time to go through Ginibre's paper, and I'd like to say a little bit now about the follow-up and how I will follow this up in my little bit of remaining time, and to be continued next week. So the first significant follow-up was in a paper of May. May's paper in Nature attracted a lot of attention, as a lot of similar papers that May wrote around about this time. Mathematical perspectives on ecological systems. His question was to do with stability. He linearized around fixed points. He had a population relating to his ecological system, and he was able to, in this linearization, he was led to consider a differential equation with a random matrix involved. He didn't know about the coupling between the ecological components, and he modeled that coupling by a random matrix. And in choosing the Gaussian case is precisely a Ginoe matrix. Now, the question of stability becomes one of the question of the real part of the eigenvalues of this matrix. If they're negative, then there'll be a decay to the equilibrium point. Otherwise, there'll be some explosion. And the mathematical question is one of the spectral radius. And to leading order, knowledge of the circular law. And you can ask finer questions, and then you have to ask more about the spectral radius. And still to this very day, questions along this line are popular research questions. So that was in the early 1970s. Ginibre's paper was cited in this context. Around about 1980, Jancovici, I've mentioned earlier, really took up questions of the significance of using Ginibre's working to underline exactly solved models relating to the two-dimensional one-component plasma. So we've seen it beta equals to I should say, Gin UE case. You've seen a direct analogy with the plasma. In Coulomb system world, you want to do different things. You want to have a boundary on the plasma. You want to be able to put some surface charge. You want to have different boundary conditions. And it was really Ginibre's calculations that allowed solvable models of one coupling only, but nonetheless typically illustrating general principles. And that'll be another theme as I continue in this today's lecture and the one of next week. Let me do that. I will say a little bit about the thermodynamic properties. And I want to do this because my own background in statistical mechanics, the thermodynamic properties are the first ones that one has in mind. Back in the 80s when I began, the big theme was really the phase transitions. Phase transitions are non-analytic points in the free energy and associated quantities like derivatives of the internal energy, etc. So one wanted to be able to access information relating to this free energy. So to introduce that topic, I should go back to Dyson's work and highlight his work in the circular ensemble case, because in his work on the circular ensemble case, Dyson, having a very broad training, was very aware that the statistical mechanics perspective that he should use his exact calculations to highlight all the thermodynamic properties. He already did that back then, and that's what I would like to draw to everybody's attention. So first, the way of thinking now is that there is a time dependence in our Hamiltonian, and we want to associate the Hamiltonian with a scattering, unitary scattering matrix. Remember before, to get led to the ensembles of Hermitian random matrices, one considered a commutation between the time reversal operator and the Hamiltonian. Well, that's slightly varied in this time-dependent theory, but nonetheless, at the end of it all, we can get some very, very analogous results. So we're asking the question, what constraints does this time reversal symmetry impose on scattering matrices generically? And the answer that Dyson found is that if we have a time reversal symmetry t squared equals 1, then before in a Hamiltonian theory, we were led to requiring the elements to be real. The analogous statement of that for unitary matrices is no longer elements be real. If they're real, we'd have real orthogonal matrices. Actually, it's requiring that the class of unitary matrices be unchanged by transpose. That gives rise to this circular orthogonal ensemble, because this class of matrices, as we can see, has an invariance with respect to transformations by real orthogonal matrices, even though they themselves are invariant under transpose. And we get similar sort of statement in this beta equals 4 case. Nothing happens for beta equals 2 when we don't impose a time reversal symmetry. We get the generic class of random unitary matrices, and we're going to, well, a feature of this theory is that there is a unique invariant measure. Before there wasn't, we had to impose a Gaussian joint distribution on the elements. Dyson wasn't happy with that, and he understood that in this unitary world that there is a unique invariant measure, and that was known here in the Haar case, and he had to construct the invariant measure in these two cases. That was done successfully, and a very clean answer came out. That very clean answer is that the joint eigenvalue PDF generalizes what I wrote down before for the Haar measure case, beta equals 2, in a very clean way, just as what happened in the Hermitian theory when beta was literally the inverse temperature in the theory. Now, because of that, Dyson went and took the time to study what I would say the thermodynamic properties. So let's go through some of those thermodynamic properties that drew his attention. Well, to set up the problem, and this is sort of important from my viewpoint of the two-dimensional one-component plasma, we want to slightly, we want to look at this a little bit differently. This is on this statistical mechanical system is on the unit circle. Oh, I should add that this is quite a sort of sideline that's been very important to my own research, and that is of the calculation of the normalization constant here. The normalization constant for beta equals 1, 2, and 4 comes out of the random matrix calculation, calculating invariant measures of knowing that the volume of the unitary group, things like that. One can ask the question, of course, for general beta greater than 0, what is the normalization? And Dyson conjectured that it has this very clean form. He observed this could be written in so-called constant term form, as a particular constant term of the Laurent expansion of a multivariate polynomial. It's created, quite a bit of interest, and it turns out to be, superimposed upon all this is Selberg integral theory. It's one of my specialties, if you like. Quite a bit that has been done in this area. So I draw that to attention, that people's attention, that this is normalized for general beta greater than naught. That will be of use in calculating the free energy and the subsequent properties. But we have to think about this slightly differently. As I mentioned, this is on the unit circle. We would like to now have our what's called a log gas on a circle of radius r. Because to take a thermodynamic limit, we want the scaling such that the average spacing between the particles of the eigenvalues is order 1. And then we do as before. We impose a uniform background. Now, we don't see any additional terms here that come from coupling the background and the particles, but that is because if we actually do the required calculation, it's because of the rotational symmetry, it doesn't depend on the position of the eigenvalues. It just contributes to the constant. But for me, in the statistical mechanics perspective, all these constants are important. You don't see them as that much in the random matrix literature, but they're very important in the Coulomb gas literature. And after doing that calculation, we get a factor coming as obtained by Dyson, and we get a further factor. Why that further factor is very important from those studying statistical mechanics is that it is the beginning of us calculating a certain asymptotic expansion, certain scaled limit, not scaled limit here, but just large N limit. Thermodynamic limit it's called in statistical mechanics. So we have a partition function. We're integrating over the actual domain. The domain here is a circle of radius r. It's really only the thetas, but the r factors are all important as well. All these factors are going. Why are they important? Because in our thermodynamic limit in statistical mechanics, we want the size of the system, the volume, to go to infinity. And for bulk scaling, we want to keep the density constant. So I want to emphasize that point. If we do that, generally, as a physical principle, the free energy should be extensive. That means it should be proportional. And the free energy is defined in statistical mechanics is proportional to the logarithm of this partition function. So we're on physical principles making a mathematical statement that the large N limit dividing by N will exist. Now that's a big topic in statistical mechanics over the years. In this exactly solvable model, we'll observe that it's true. And it's important to us. So I won't go over time because we have another lecture coming up next week, but I do want to highlight the quantities that we're going to be interested in calculating in the two-dimensional case to the extent we can. In statistical mechanics, a key quantity is the pressure. So we've seen our partition function. We've related that to the free energy. We can directly calculate the pressure if we vary the volume from the logarithm of our partition function. Now that generally is a non-trivial calculation. It can, in the large N limit, or the large volume limit, I should say, it's a derivative of this free energy per particle with respect to the density. Now in the one component plasmas, it actually is a trivial calculation, which is quite remarkable. It's a trivial calculation because the way we've set up the problem by putting our volume, scaling, which is not part of the random matrix setup, the volume, why it needn't be part of the random matrix setup really is that it's sort of scale invariant. The volume factors, we don't need to know the logarithm of this configuration integral here. We have for free what the pressure is, although it's a little bit disturbing from the viewpoint of physics. Why is that? The formula we get involves this factor 1 minus beta on 2. 1 minus beta on 2, as we vary beta, could actually go negative. And our physical intuition as pressure as force per unit area is disturbed. So we have, for one component systems, the so-called thermodynamic pressure as calculated from this formalism is different to the mechanical pressure. And people over the years in Coulomb systems have written about this. It's because of this inert background. In our formula for the thermodynamic pressure, the inert background has not been, is being varied when it shouldn't be varied. We should only be varying the actual volume with respect to the mobile particles. So this point's understood, but it's very much worthy of drawing attention to, that there is this simple formula for the thermodynamic pressure. But it tells us beta equals 2 is very special already, for example. Something that's less contentious in the sense easy to interpret without any strange points is internal energy. Internal energy, average of our total energy here, average over the ensemble. It's calculated by a derivative with respect to the inverse temperature, the beta variable, and can be calculated if we know the free energy per particle. And that's precisely what we know because of the Dyson constant term identity, X conjecture now. Dyson had that conjecture available. He made it. And from that, he can calculate this limit. He proves that it exists. So it's an asymptotic expansion from our perspective. We're saying the leading term of the logarithm of that this quantity here is proportional to n. And he tells us what that term is, and it's a physically interesting quantity. And as I've already said, the density scales out. We see in random matrix theory a fixed value of density is more. We don't usually put the density in, but it is important from a statistical mechanics viewpoint. And when I come to the two-dimensional case, and I'll finish soon, see that the hour is almost up, this same feature will be important. I want to draw attention to an aspect that is really not known in the two-dimensional case. Here, energy per particle is a specific functional form. It's proved to be analytic for all beta greater than naught. And from a statistical mechanics viewpoint, and my mindset coming from the early 1980s when phase transitions were all important, is very much on this point here. The phases of the corresponding statistical mechanics system. We have a temperature variable. If we lower the temperature, even for this particular Coulomb, this log gas on the circle, we're going to attempt to converge to a crystalline phase. The crystalline phase is very simple on the circle. The particles are equally spaced. And the question of interest is there a sudden transition to that crystalline phase or a transition which is non-analytic in beta? And the interpretation of that would be that we've gone from a fluid phase to a solid phase. And this is one of the very prominent questions in the theory of the two-dimensional case. Computer simulations right from the 1980s right up to now, there haven't been any change of the results, even with the exponential improvement in computing power, indicate in the two-dimensional case that there is a phase transition, that there is a solid phase as distinct from a fluid phase in the two-dimensional case. It's unfortunately not accessible by analytic calculations, but it is an interesting theme, and I will be following that theme up in my next lecture. What I'd like to conclude with right now, I do have a lot more slides, but I won't. I'll leave them until the next lecture because I'm out of time. Interrelations between a thermodynamic quantity, we've just seen it up here, the energy per particle, and our correlation function. So the claim for a one-component system, and unfortunately, this is not at the level of a mathematical theorem. Statements like this are in books on theory of fluids, Hansen and McDonald from, they've got a second edition of their book. They're very well known. They relate Monte Carlo simulations to quantities that can actually be calculated. Very interested in formulas of this sort. It's very difficult, perhaps, to sample energies literally, but one can indirectly calculate it. The claim is one can indirectly calculate. So if all that's been done here is some interchange of limits, but as we know in analysis, it can be very challenging to prove that this interchange of limits is justified. But it's taken in the theory of fluids as given that it's possible to alternatively calculate this internal energy just by averaging our connected part of the 2-point function with respect to the pair potential. Remember, the system's a little bit more complicated generally. We have a, because of the background, we may have a harmonic attraction to the origin. We don't see that in this formula. We just see the pair potential. We can check that it's consistent. And Dyson mentions parenthetically that he has done an alternative calculation. And it must have been this very calculation. This is going to be very important for us in the two-dimensional case because we don't have a function of beta. We only have beta equals 2, the free-Fermi point. We don't therefore know how to do a derivative with respect to beta. So the most natural way of computing the energy per particle, which, as I mentioned, can be compared against Monte Carlo simulations, is through this formula, and that has been done. Well, I've gone a little bit slower than I hope, but nonetheless, I hope I am setting to the scene, or at least my way of thinking from the early days of the my own time, long time now, decades in all matters related to Ginibre ensembles, heading in a particular direction that both is part of the heritage of Ginibre's paper and is also, to an extent, at the fore of current studies. On that note, let me pause and thank everybody for their attendance. I will continue from this point on with further material this time next week.
Yeah, thank you very much for your inspiring lecture. Any questions or comments? So you can turn on your mic and then ask any questions, or you can leave a question in the chatting room. Mario Keyberg.
Thanks a lot.
Yeah, you have a question, right? Yeah.
Exactly. Thanks a lot, Peter. I have a question actually regarding, since you, well, more or less, you scavenged a bit, quite a lot of literature. Maybe you came across that, namely, what I always wondered is, since when you start from Ginibre, you don't look really at the cases where the matrices are not diagonalizable, right? Where the Jordan blocks are larger than only one-dimensional, because, well, exactly these cases are, well, of measure 0. However, did you come across some kind of literature where actually these situations are also studied? Since I would say, because of the size of the Jordan blocks, you can then give each of, well, these particles individual charges, something like that, right? Because, well, they appear several times, the point.
Yeah, no, thanks for your question there, Mario. There is some literature on generally singular sets. So in random matrix theory, yes, even going back to the Hermitian case, we sort of exclude the possibility of degenerate eigenvalues. So one can sort of enforce that, in what you're implying in the non-Hermitian case, and ask for the volume in some conditioned space. And people have certainly done that. I haven't got at my fingertips the actual papers, but I have come across them. As far as the specific question you're asking about related to Jordan blocks, again, it's in that class of singular sets.
I would
sort of start there, yeah.
Yeah, I would expect that starting, say, from Ginibre matrices and then adding these additional conditions, you should have somehow some kind of induced density exactly on these, let us say, since they are nothing more than boundaries of these Weil chambers, right? Exactly.
Yeah, very much. Well, for me, in the Coulomb gas perspective, I'm most interested in these degeneracies because they act like some accumulated charge. If we, what I call spectrum singularities, if we condition to have a degeneracy of multiplicity Q or something, to me, in Coulomb gas world, that's like having an external charge Q. The type of conditioning that you're hitting at I can wonder if there is a Coulomb gas interpretation. But I do very much appreciate your question in the sense I understood what you say, very much understand what you're saying, and I will keep looking out, make some notes on literature along those lines. Yep.
A lot, Peter.
Thank you.
Any other questions or comments? Meng Yang, Dr. Meng Yang, yes.
Yeah,
Okay,
so
go
I
ahead.
have a quick question because first of all, thank you for the interesting talk. And also like at the end of your talk, you mentioned the partition function for circular ensembles. Like for 2D Coulomb gas about the partition function, do you think if back to like 1960s, whether they think that's an interesting question to answer, or like for next week, will you like continue for this partition function for 2D Coulomb gas?
Indeed, it was my intention today to conclude with the story of the partition function. Is an interesting question. Well, being trained in sort of mathematical physics, Dyson realized that the chances of obtaining a theory for general beta are rather slim, and he, as people do in mathematical theoretical physics, was most interested in limiting cases. So limiting cases for us, we have high temperature, we have low temperature, we also have a special point, free Fermi type point. And then he'd be interested in asking questions, expanding about that. Now, I think it is very prominent because for low temperature, as I was saying verbally, we do get a crystallization in the one-dimensional model to equally spaced points. In 2 dimensions, it's believed, and it's close to a theorem, that a triangular lattice appears. This is going to be the last of the slides on this series here. So that's a bit of a deal in mathematics, the crystallization conjecture, it's called. And there is a very precise conjecture for the ground state energy here. So there is a whole world of studies of people in topics relating to energy minimizations. And this Coulomb gas gives a very clean and structured mathematical content here. The slide before will tell us that the conjecture goes via another class of particle systems called Riesz potentials. So in the modern literature, there are people studying the particle system with the Riesz potential. Now, the other limit that comes up physically is the high temperature regime. That's what people in the theory of fluids call weak coupling, and it relates to what has been known for nearly a century now as Debye-Huckel theory. So there's a type of mean field theory, and it gives rise to this correlation length, etc. From a mathematical viewpoint, that physical picture gives some opportunity to develop a theory at high temperatures. And in a topic that I was interested in back in the early 1980s, constructive quantum field theory, there are a number of people who are trying to make a rigorous theory of weak coupling, high temperature, mean field theory for Coulomb systems. It's still a little bit of a frontier. It's, there's some issues with the requirements of renormalization and such. And it's why it's a topic that people expert in quantum field theory have studied over the years. That is being suggested by these solvable cases, the limits one can take. And as I mentioned, for us, we have these special random matrix points related to free Fermi. But underlying, we have these high, low temperature limits that I believe are somewhat at frontiers of modern research. In Coulomb systems, I add to that.
All right. Okay, thank you so much.
Thank you.
Thank you very much. Any other questions or comments? If there's no, let's thank our speaker again. Okay, so we will meet next week at the same time. So Peter will continue to give his wonderful lecture next week. Okay.
Thank you.
Thanks, Peter.
Thank you, Peter.
Great. Bye-bye.
교수님 나가신 거지?